Welcome to MathStat341, lecture I think 6. What I want to do today is talk a little bit about mathematical modeling. So this is, I'm not bothering to change the date or the room location. This was some joint lectures I gave in a merging of both a probability stats class and a mathematical biology class. So some of the examples may be more biological than I would normally have chosen myself. The idea is, how do we use probability to actually solve problems we care about? How do we formulate, and then once we have the formulation, how do we actually solve it? All right. So I will quickly review some probability. I may introduce you briefly to some differential equations and difference equations. Out of curiosity, how many people have taken differential equations? Okay, not that many. It's not a bad thing to see. There's a lot of nice techniques and tricks to solve a variety of problems. I'll talk about how to solve some difference equations. We actually saw a little bit of this already when we did the Fibonacci numbers. So some of these slides will actually look more than just a little familiar if I did a good job. And it's much easier to do that with slides and having to do all the algebra and not make a mistake on the board. And then I will do some applications. How many of you have ever played or know the theory of roulette? I will show you why you should not go to Vegas and gamble on roulette. All right. Background. So if you took a calculus class where you did areas under curves and they never mentioned the word probability, you have a case to prosecute. Depending on who's on the jury, you might even get a conviction. Okay, I believe it is criminal to do an entire calculus class with areas without saying the word probability. Why do we care about areas? We care about areas because so many times these areas represent probabilities. And we can use this for probability, we can use this for statistics, we can use this to calculate the likelihood of events. So X would be a random variable with density P. Sometimes we'll use the letter F, dare to be different. Sometimes we'll put a subscript capital X to denote that it's the density associated to the random variable X. If you only have one random variable, it's not really needed. If you have multiple random variables, however, it's actually quite nice to be able to quickly glance down and see what the density is associated with. So here are the conditions to be a probability density. You must be non-negative. The area under the curve must be 1. And then the probability you take on a value between A and B is just the area under the curve from A to B. And so I've highlighted it over here. The mean or the average values, I just integrate X times the probability. The variance of how spread out it is X minus the mean squared, so that I have something that's non-negative. The larger the variance, the more spread out things are in a certain sense. You could, of course, have discrete distributions. You could have things that are a mixture of discrete and continuous. For now, I'm going to just be dealing with continuous distribution. And then independence, knowledge of one mean variable plus it gives no knowledge of another. So how many of you ever watched The Price is Right? So they have a showcase showdown where you have a wheel where you have numbers from 5 to 100. And whoever gets closest to 100 without going over advances. When you spin the wheel, it stops. And if you don't like a number, you can spin again. Are the two spins independent?
Oh, no.
No. Why not?
Because you only spin again if you don't like it.
So you might spin only again if you don't like the number, or you might be trying to get a certain number, so you might adjust the force of your spin. You're not starting from the same place. Now, I believe the Red Sox are playing tonight. Do you think the outcome of the Red Sox game depends on how well I lectured today? God, I wish that was the case. Right? Those should be independent events. Okay? So we really want to understand which things are independent, which things are dependent. If I roll 2 fair die, we normally consider the 2 die are independent. If I glue them together, have like a little rod connected to them, then they will be dependent. So the big result is the central limit. Yes?
If you roll the 2 die at the same time, could you argue that they are dependent?
Well, it could matter in terms of how you put them in your hand and how you do the motion. You could absolutely argue that they are dependent. That there will be some, in fact, it could be an interesting experiment to try to roll the same way, hold the die the same way, and see what happens. Do that 100 times and just see, does it look dependent or not? There are people who practice flipping a coin so that they can flip a head. It's not a bad skill to develop. You've got a valid point, I've got a valid point. Let's just flip a coin. I'll call heads. And if you can flip so that it looks like it's truly random, then you're in great shape. All right. So biggest distribution for us in this course is going to be the standard normal, or more generally a Gaussian or a bell curve. When you have this many names, you are important. Okay. Either the negative x minus mu squared over 2 sigma squared divided by the square root of 2 pi sigma squared. You'll see later why this integrates to 1, and it is a probability distribution. It is clearly non-negative. And the big theorem in the class is the central limit theorem. If we have a bunch of independent, identically distributed random variables with mean mu variance sigma squared and finite higher moments, there's wicked conditions you can do, then if I look at the following sum, it converges to being normally distributed with mean 0 variance 1. What is my sum? I added my random variables, so that's the sample sum. I then subtract off n times mu. Well, if each one of them on average is mu, if I have n of them, I expect to have something of size n mu. So the numerator should be something of size 0. And dividing by the sigma root n, that should be now give me something of size 1. Something with standard deviation 1. The idea is we want to study apples and apples, not apples and oranges. So by doing this standardization, I now have something that's converging to mean 0 variance 1, rather than having something that converges to a normal with ever-increasing mean and ever-increasing variance. So this is the central limit theorem. Now, how many of you have taken a stats class? How large must n be in a stats class for you to say the central limit theorem kicks out?
Should we get at
least 20? 30? I prefer the at least 30, you're a little bit safer, but then you might have a harder analysis if you're a little bit lower. So the question is, for which distributions is 20 or 30 close enough to infinity that we can actually say, yeah, it's a normal? What's the easiest distribution you can think of? No, the normal's not the easiest. Easiest. Uniform. So if you roll one die, you get the numbers 1 through 6, each one with probability 1/6. So I'm going to compare the normal to a uniform, and I'm going to adjust them so that they both have the same mean and the same standard deviation. What do you think? Good fit, bad fit, okay fit? It's not horrible, but it's not phenomenal. Now, what if we do two uniforms? Well, if you think of rolling 2 fair die, you get sums from 2 to 12. 2 and 12 happen 1/36 of the time, all the way up to 7, which happens 6/36 of the time. You actually get a triangle function. And in fact, more generally, if you have two uniforms that are continuous, when you add them, you get the following. Good fit, bad fit. It's not horrible. Building on our success of sums of 2 uniforms, what should we do? No! 4, yes. And then after the success of 4, what should we do? Say yourself. 8, there you go, right? Because if we do sums of 4, we already know the distribution for the sum of 2. Then we could take the triangle and add a triangle to that. Whereas if we did 3, we would have to take a triangle and add a rectangle. And so if we do sums of 4, well, now you're getting to the curvature. This is looking pretty good. If you get up to 8, really good. And again, this is for the uniform distribution. So this is not so bad. Now, why are we going to be spending so much time and developing so much theory to prove the central limit theorem? The standard normal is a nice function to work with. Here is the explicit formula for the sum of 4 uniform random variables. Okay? And the nice blue text, don't even think of asking to see the sum of 8. This is the answer. Do you want to work with this? Hell no. You would much rather say, screw this, it's approximately a normal, let me just use the normal, and I'll be pretty close. And it's much easier to work with that than to work with the 1 over 54 times 72 minus 36 root 3y, but this is only, et cetera, but this is only if y is between root 3 and 2 root 3, right? So this gives you some sense of the power of the central limit. We don't have to do calculations like this. We can replace them with the standard normal. All right, introduction to difference equations. So these are discrete versions of differential equations. If you've seen Newton's second law, F equals ma. Acceleration is the second derivative of displacement. So this is a second order differential equation. Second order differential equations occur frequently in physics and the natural sciences. Difference equations are discrete versions of differential equations. You have a discrete time step in which things happen. And so we're going to say an is going to be a function of the previous L states. So you have finite memory. In a chess game, does it matter how you got to a configuration on the board, or does it just matter what the board is? So this is who really knows chess. It slightly matters, because in chess, if there's a threefold repetition of the board, it's considered a draw. I don't think checkers has that rule. Backgammon doesn't have that rule. So for a lot of games like that, like backgammon or checkers, it doesn't matter how you got there. It just matters where you are now. And it would be a completely memoryless process. In chess, there is a little bit of memory that matters. So if we look at the Fibonacci, this would be the case L equals 2, and Fn depends on just the previous two, one of the simplest possible relations. And then we have initial conditions. More generally, these are a large class of difference equations which are applicable in the real world. They model things we care about, and they're very easy to solve. So you have a finite length, and the coefficients are constant. If the coefficients depended on n, much, much harder. But if the coefficients are constant, it's not too bad. So we can compute these. So how many of you have seen matrices and Fibonacci numbers? All right, so here's a way to review some of the stuff from linear algebra. This is a prereq for the course. Let me show you how you can actually use linear algebra to solve the Fibonacci's. And then we'll generalize this to actually apply to real world. Let's consider the vector Fn plus 1 Fn. And if I take the matrix 1, 1, 1, 0 and act on Fn, Fn minus 1, then the top becomes Fn plus Fn minus 1. Oh, that's Fn plus 1. And the bottom is just Fn. So this matrix is a transition matrix. It takes us from a pair of Fibonacci numbers to the next pair. And so we gotta have this matrix formulation. So Vn would be Fn, Fn minus 1. And then Vn plus 1 would be AVn. It's also A squared Vn minus 1, all the way down to AN V1. And this is similar to the binomial coefficients. I want to make sure I stop at the right point. I notice that I have 1 plus n is n plus 1, 2 plus n minus 1 is n plus 1. So I want to go all the way down to V1. I should have n powers of A here. You want to make sure you have things done correctly. What this tells us is I can compute any Fibonacci number if I can compute high powers of a matrix A. Now we can use linear algebra to solve. So you've hopefully seen eigenvalues, eigenvectors, orthonormal bases. Here's an example of why you give a damn. It's actually nice when the math we give you can be used for something. So what you would do is you would actually decompose the vector v1 in terms of the eigenvectors of the matrix A, figure out where the corresponding C's are, and this is one way to get Benet's formula. Right, so I'll leave that as an exercise to you. And we've already remarked how much Professor Miller loves this formula. It does not look like an integer, but it is always an integer. You can ask, what can you replace the 5s and the 2s with and still keep it as an integer? All right. So let's imagine we have a population of reals. And I will give cultural extra credit if anybody knows why the reals are named George and Grace from the 1980s movie. George and Grace. All right. So we have a population of reals with the following assumptions. I should be more serious. You always die when you are 4 years old, never earlier. Reasonable or unreasonable? Unreasonable. Each pair of reals becomes pregnant when they turn 1 and gives birth to 2 pairs when turn 2. And then each pair becomes pregnant when turn 2 and gives birth to 1 pair when turn 3. That everybody's reproductive cycle is perfectly aligned. You always have the same number of, I think they're called calves, as all other pairs of whales. Do you think this is reasonable or unreasonable? This is the greatly simplified model of real population dynamics. Okay? We will solve this first, and then we'll say, well, how can we do something that's a little bit more reasonable? But if we can't even do this, then we're in trouble. So this is just general advice. Keep the model as simple as possible. Later in the semester, I will talk about some of the work I've done in sabermetrics in baseball analysis. And I will have a model, and basically, depending on how much time in the class, that's how many mistakes you will find with the model, how many unreasonable assumptions. but they're not horrible, and a lot of things kind of cancel out. So what's the simplest model we can analyze? And then let's start adding the bells and whistles. So can we figure out how many wheels of each age are there at each moment? So we assume we know how many wheels there are at each age. Well, we can't, because this is completely deterministic. That's why this is so unreasonable. Right? The real world is not completely deterministic, but it's often not a bad start. So we're going to set up a system to describe the population. So AN will be the number of pairs born in year N. So I'm not talking about individual wheels, I'm talking about pairs of wheels. If it bothers you about somebody mating with a sibling, we will have them just immediately swap, whatever. Okay? So I'll just always be talking about pairs. So BN will be the number of pairs that are 1 year old in year N, CN will be the number of pairs that are 2 years old in year N, and DN will be the number of pairs that are 3 years old in year N. And we just want to figure out how the population is at time N plus 1 year later. So which of these is very easy to figure out the value of N plus 1 in terms of the values in terms of year N? Yes?
Well, like for BN, CN, DN, we just check the previous years. Like
Yeah, so BN plus 1 is just going to be AN, and CN plus 1 is just going to be BN, and DN plus 1 is just going to be, and then for AN plus 1, well, that's just the reproductive stuff. And so you get AN plus 1 is 2BN plus CN, BN plus 1 is AN, CN plus 1 is BN, DN plus 1 is CN. Okay. Now, this is a perfectly fine way to write it, but it's not illuminating. A lot of this class is trying to talk to you about how to write things in a more illuminating manner. If I write it like this now and I expand things out, doesn't this look like a matrix form problem now? And it's screaming at you, please define a matrix like this, so that my new vector N plus 1 is this matrix applied at time N. Or if I keep iterating, it's the matrix to the N plus first power applied to the initial state. And now we can see what the population is at any moment in time by just computing high powers of this matrix. So these matrices are called Leslie matrices. They're actually a very famous structure matrix. Does anything look interesting in this matrix? Yeah.
It's a series of ones.
So there's a series of diagonal ones, and that's basically saying how something is just moving to the next level and shifting down. Good. That's one of two things to observe. And remember to email me when you observe. Yes. There's also this column of zeros. And biologically, what this means is that the wheels that are 4 years old are really not doing anything useful. If you want, you can just shoot them. They're no longer involved in the evolution. I said if you want to. It turns out in the movie I'm talking about, it's very bad if all the wheels die. Humanity will be destroyed by an evil alien probe. Well, I shouldn't say evil, by an alien probe. So trying to give you some clues.
So it's not Ace Ventura.
No, it's not Ace Ventura. If it was Ace Ventura, we'd be talking about the dolphins, exactly. But I mean, I am trying to give you some clues. But it's a Leslie matrix. The fact that we have all zeros over here, let's do it with this. See. The fact that we have all zeros over there basically is telling us that from a biological perspective, the wheels of age 4 aren't doing anything. And for a lot of species, they actually, if they don't have any interactions with their kids, not everybody's lucky enough to coach their kids in baseball. Once the kids are born, the parents leave, they're no longer really involved at all. You can ignore them. So in some sense, we don't necessarily need to be keeping track of the DNs. If you wanted to know how many wheels there are, yes, we need them, but they aren't playing a role. Now, what role might the older wheels play?
Competition.
Competition, so the older wheels might be eating food the younger wheels need. Another good reason to kill them. Can we give a reason why we might not want to kill the older wheels? What could they be doing?
I thought population control, but also like that completely defeats the whole idea of wheels dying at the age of 4.
Right. But what could be a benefit of having wheels that are of age 4? Yes, I mean, as somebody who is more than 4 years old right now, I'm very happy that we can start to find some reason to keep old people alive. I thought Professor Miller was saying we should, so just being very clear, please do not go out and kill people, whales, anything, and claim that you learned this in MathStat341. So they could be giving life experience. Also, if there's predators, maybe the predators will go after them and not the younger ones. So, they could be like decoys. So there could be many reasons to keep these older whales alive. So is this form reasonable? We talked a bit why this form was reasonable. And here's some mathematical code to just analyze it. We've talked about some of the problems with this model, right? You're always living to born and dying. You're always giving birth exactly at this time with this amount. And there's no problem with resources. Okay, eventually, the entire Earth will be populated by whales. And then the population would continue. So what's the solution? Random variables for entries. So now what we can do is we can take something of the same form. What do you think the numbers S1, S2, and close?
Close to 1.
They should be close to 1. Which side of 1 should they be on, above or below? Below. You should not have wheels emerging out of nowhere. Like, look, we got a new wheel that was 3 years old. There's only one book I know of where a wheel emerges out of nowhere. Extra credit, cultural extra credit. The big line is, oh no, not again, and there's a petunia involved. No, not none. There is one book where a wheel emerges out of nowhere. Hitchhiker's Guide to the Galaxy, it's the infinite improbability drive, so it is related to this class. That's the only situation I know, and they're invoking an infinite improbability drive to have a wheel emerge from nowhere. So the S's should be random variables that are less than or equal to 1. Or maybe you write them as 1 minus something, and it's 1 minus a positive number that's at most 1. They should not be negative numbers. So this is a more plausible model. Can we study something like this? And now we typically use capital letters for random variables, lowercase letters for their values, and we're setting some notation for the course. So we could let these be the reproductive rates, we could let the S's be the survival rates, and we would then end up getting products of matrices like this. And now the question is, what can we say about products of matrices? And you can begin to see the different tools that are needed to do the analysis. Products of matrices are extremely difficult. We're not going to do much with this, but I just want to throw this out. This is another truly beautiful formula. So the commutator of two matrices, bracket A comma B, measures how far A and B are from commuting. It's AB minus BA. If they commuted, this would just be 0. And it turns out that we can extend the notion of the exponential function, and instead of putting in a real number, we can put in a square matrix. And because the factorial grows so rapidly, this matrix sum will always converge. And if you wanted to multiply two matrices, if I look at e to the a plus b, you would say, well, isn't that just e to the a times e to the b? Only if the matrices commute. If they don't commute, you then have e to the minus a over b over 2 term, and other ones involving commutators of commutators, and then commutators of commutators of commutators. And you can see we like things that commute. It makes the analysis a lot easier. Frequently, a lot of the models are chosen because they lead to more tractable mathematics. That's the main point I want you to get out of the slide, is frequently people will choose things that will lead to an analysis that can be done. Okay. A little bit on efficient computation. So we've talked about Benet's formula. We've done this before, so I'm not going to do too much on this. I'm just going to very warp speed go through the slide. We talked about how Fn is between twice Fn minus 2 and twice Fn minus 1 by just replacing things. So we've got an exponential growth rate. It goes at least as fast as root 2 to the n and no faster than 2 to the n. So it's not unreasonable to try Fn equals r to the n. And this is how you solve a lot of difference equations. You guess the method of divine inspiration, and then you show your guess work. So we'll try Fn equals r to the n. All right. This is going through the slides using the generating functions. Since we talked about those, I'm not going to actually go through this again. This does the algebra, partial fraction expansion if you love, the geometric series for each one. This is another way to get to Benet's formula. All right. So we've talked about how generating functions are important. They bundle things together. They give us a global object, and the idea is to try to deduce local information from the global object. We talked about various sums. Here's another nice one. Fn divided by 3 to the n is 3/5. Or is it 3 over 120? Which is it? Is it 3/5 or is it 3 over 120? Is the 5 factorial 120? Or is it just, I'm excited that the answer is 3/5, right? You really want to think about notation. Sentences should end with punctuation. If I was excited, I put an exclamation point. If I wanted 5 factorial, I should have a period after that. What if I'm excited about it ending in 5 factorial?
Double.
Right, now the double factorial actually means something. Double factorial means every other. So 5 double factorial is 5 times 3 times 1. 6 double factorial is 6 times 4 times 2. So if I did 5 factorial, if there's no period, I might say I'm probably excited that it ends with a, but this is like, I should probably rephrase this. Now, this is a ridiculous example. Why am I talking about this? Because there will be times when you are doing writing when it will not be ridiculous and it will not be clear necessarily what is being meant. So I really want you to think about how you express things, how you write things. Right? But when you're writing a technical report that people need to act on, be very clear, be very focused, be very deliberate in what you write. All right. So roulette. How many people have ever played roulette? Okay, good that there's not too many people. Although if you're just playing for fun, that's fine. All right. We're going to play a simplified version of roulette. Now, the actual version in Vegas and casinos is not kind like this to people. But if we can't even win in the nice kind version, we're dead in Vegas. So this is a classic probability problem. In fact, a lot of probability was inspired by people trying to understand games of chance. So here's a typical roulette board. You have 36 numbers, half red, half black, and then you have 2 greens. So the greens would be the 0 and the double 0. And there's different types of bets you can do. You can bet that a red will come up, or you can bet that a 7 will come up. Various things like this. What's the probability a red comes up? Is it a half, more than a half, less than a half? It's a little bit less than a half because we have the 2 greens. And that gives Vegas a little bit of an advantage. When Vegas sets the payout rate, they set the payout rate based on a red being 50% likely. We will assume that there are no greens for the sake of argument. Now, Vegas does a lot of truly remarkable things. I'm going to be very careful how I phrase this. There are 2 main types of morons who spend a lot of money on roulette. There are the morons who go, red has come up 8 times in a row. Red is on fire. I want to bet on red. What's the other type of moron?
It's come up 8 times in a row, it can't come up again.
It's going to be time to bet on black. Right? Vegas doesn't really care which of the 2 flavors of moron you are. All they care about is that you are the type of moron with money who will put money down. In fact, in some places, they now announce what the last couple of spins are to try to, ooh, red is on a roll. Because they know if just enough people are playing, the laws of probability are on their side. The phrase is, somebody has to pay for Mr. and Mrs. Smith's suits. Right? This is not a charity in Vegas. Someone is paying all these salaries. Where is that money coming from? So here is a strategy. We'll assume that red comes up half the time. This is called double plus 1. Has anybody heard of double plus 1? So when I was young, my father heard about this. He was, wait a minute, this sounds good. And he actually wrote a program in BASIC to simulate what would happen. You know, he didn't know how to do the actual theoretical calculation, but he could write code. It was, oh, this will not work. But at first, it sounds like this can't lose. Where am I today right now? I'm here. I'm not in Vegas, right? If this was a sure go brainer, I certainly would not be here, or if I would not be wearing a shirt that's got rips and whatnot. I deliberately chose it. So here's the strategy. Bet $1 on red. If red wins, you're up $1. If not, you're down $1. So if you lose, bet $2 on red. You lost $1, just made 2, so you net $1. If you lose, you're down 3. How much should you bet if you're down 3? $4. If it comes up red, you win, and you net $1. If not, you're down 7. If you're down 7, what do you bid? 8. Lather, rinse, repeat, the shampoo method of mathematics. Eventually you win $1. And you repeat this and you win another $1. And if this is too slow for you, just multiply everything by 1,000 or 100,000. What is wrong with this idea? There's got to be at least something wrong on here. Yes?
The numbers get pretty large.
Yes, and?
Well, unless you just have infinite much.
Okay, so there is a small little issue of you might need to have an infinite reserve. All right, that is one issue. So why am I not at Vegas? So as mentioned, the bankroll. So for instance, here's how much you would have to bet. And if you get 20 consecutive blacks, you're now betting $1 million. I had to try and get $1 million, not a problem. You know, I know Williams alums. But there will be a limit to what I can get my hands on easily. Yep. If it was a guarantee, I can get the $1 million, $10 million without any trouble from the Williams alums. Probably even $100 million. $25 quadrillion? No. Yeah, there is an issue. Now, how many of you have taken economics? So you're used to unreasonable assumptions, correct? So we will have the eccentric rich uncle aunt hypothesis. So I posit the existence of an eccentric family member who has an essentially infinite bankroll, and whatever money you need to keep playing, your eccentric aunt or uncle will give you that money. They will not give you $1 direct. They want you to work for your money. But they will bankroll you. They never want you to be denied an opportunity because you don't have the money. So if you need $15 quadrillion, they're there for you. Is this enough to allow us to win at Vegas? Because now we can always make the bet.
Can you always get the bet?
And that's the next problem. Table limits. Trust me, Vegas knows mathematics. They know probabilities, they know difference equations, they know these calculations. They set strict table limits as to what is the maximum distance from the minimum to the maximum bet. So let's say the table limit has a lower value of 5 and an upper value of 200. Then as you keep doing things, well, I should really divide by 5, so now it's going from 1 to 40. I can get up to 32, but then when I try to bet 64, I would break the limit. And so they choose this very carefully to make sure that you hit the table limit. When you win small. When you lose big. So if a bunch of us were to go, with high probability, a lot of us might actually leave Vegas with some money and a profit. And some of us would now be no longer enrolled at Williams College, or would now be on massive financial aid, something like that, because their family's resources would now be sucked up into Vegas. That's the whole point, is that the wins don't necessarily have to be spread evenly among everybody. They can concentrate. And so here, if we start off, if the table limit was somewhere a little bit more than 128, when we get to the 256, we couldn't make that bet. So it all comes down to what's the probability we have a huge number of blacks in a row if we're betting on red. If the probability is very small, then I can go to Vegas and I'm not worried if I can have a reasonable bankroll because it's very unlikely to get 5 consecutive blacks. Well, what is the probability of 5 consecutive blacks? So I'm going to let Pn be the probability we will not get 5 consecutive blacks, and Qn will be the probability we get 5 consecutive blacks. And the n is going to be a number of spins. The uppercase n turns out to equal the same as the lowercase n. This was a typo. And I'm saying Pn plus Qn equals 1. Well, yes. If I look at the probability I do get 5 consecutive blacks and n spins, and I add to that the probability I don't get 5 consecutive blacks and n spins, then that should sum up to 1. One of these two events should happen, and these events are mutually disjoint. I can't both get and not get 5 blacks and n spins. Okay, now if n is small, like 3, what is P3? What is the probability we don't get 5 consecutive blacks and 3 spins? 1. Small values we can compute very easily. We can actually write down a recurrence relation. So hopefully this is readable. We start off with Pn, and then on my first spin, one of two things happens. I either get a black, and I end up over here, oops, or I get a red, and I end up over here. If I get a red after my first spin, how many spins are left? How many spins are we doing? Sorry?
So we have 4 left.
No, we're trying to either get or not get 5 consecutive blacks. So Pn is the probability we do not get 5 consecutive blacks. If we start with a red, could this be the start of 5 consecutive blacks? No. How many spins are left? How many spins are we doing total? No.
Well, n minus.
Well, no, how many spins are we doing? We're doing n spins. How many spins have we now done?
1.
1 spin, right? We just got a red here.
Oh, I thought it didn't. We got it right. We want that.
Well, no, well, we don't. We want to calculate the probability. So Pn is the probability we don't get 5 consecutive blacks. So our first spin here is a red. Our first spin on the other side is a black. We have n minus 1 spins left. Given that the first spin is a red, what's the probability we don't have 5 consecutive blacks in the remaining n minus 1 spins? This is the hardest part of the problem. So Pn is the probability we don't have 5 consecutive blacks in n spins. What's the probability we don't have 5 consecutive blacks in n spins, given that the first spin is red? Pn minus 1. It's now, we can forget about this. This is a place where we can forget about this, and now it's like we're playing the game with just n minus 1 spins. This should remind you of the Bird-Johnson game. You know, the shooting baskets. We can forget about what happened now, and now we're just playing a game with n minus 1 spins. What about if the first spin is a black? Can we forget about that? Is it more or less likely now to have 5 consecutive blacks if the first spin is a black? It's more likely. So let's spin again on that side. And there's 2 possibilities. We get either a red or a black. Now, we've done 2 spins. What's the probability if the first spin is a black and the second spin is a red that we end up with 5 consecutive blacks?
P of n minus 2.
P of n minus 2. And then over here, we still have to worry about that. And so you can keep going on and on and on. And then we could do black, black, red, black. And then this possibility could go black, black, red. We now have n minus 3 spins to go. Since we start off black, black, red, it can't begin 5 consecutive blacks. So the probability that we have 5 consecutive blacks, given that we start off black, black, red, is just going to be Pn minus 3. The next one will be Pn minus 4. The next one is Pn minus 5. Oh my God, how long are we going to have to do this? You know, the image is getting harder and harder to see. Do I need to go further? This is probably the easiest probability question I can ask you. Given that the first 5 spins are black, what is the probability you do not get 5 consecutive blacks? 0, right? You start off with 5 consecutive black spins. What's the probability you don't have 5 consecutive blacks in your n spins? 0. That's why it's much easier to look at Pn than Qn. Qn is the probability we do get 5 consecutive blacks. If we did a Qn, we would have a 1 over here. And that would not give us a recurrence relation with fixed depth and constant coefficient. There are things you can do, there are tweaks you can do, but this is a little bit easier. So it's just a nice 0 over here. And now we get a recurrence relation. So Pn, the probability we do not have 5 consecutive blacks in n spins is going to be, how often are we in this case? Where we have just a red after our first spin. How often does that happen? Half the time. It's going to be 1/2 Pn minus 1. How often are we black-red? 1/4 or 1/2 squared. And then et cetera, all the way to 1/2 to the 5th Pn minus 5. So this is going to be a recurrence relation of depth 5. All we need is the initial conditions. What's P1 going to be? The probability we don't have 5 consecutive blacks in one spin. 1. In fact, P0, P1, P2, P3, P4 are all going to be 1. And this will allow you to calculate P5 is a half plus a fourth plus an eighth, which will be 31/32. So the probability we don't have 5 consecutive blacks in 5 spins is 31/32. That makes sense. The only way to have 5 consecutive blacks is 1/2 to the 5th or 1/32. So we could actually use this and just march down. You could have an Excel spreadsheet, and essentially you just have this weighted sum of previous terms. And if I want to calculate what's the probability I get 5 consecutive blacks in 100, I can solve this very fast. I could do the generalized Binet formula for something like this, but it's not worth it. So we talked about the initial conditions, and then here's some code to try to solve it exactly, and here's the closed form expression with approximations. Here's graphically a plot of what happens as we take more and more spins and gets larger and larger. With 100 spins, you have about an 81% chance of having 5 consecutive blacks. If you have 200 spins, the probability is 96.59%. So you have a tremendous probability of getting 5 consecutive blacks somewhere in 200 spins. So when you lose, you're going to lose big. Okay, and you can see, do you think this is ever going to get larger than 1? No, it's going to asymptotically approach 1. No matter how rigged the games are in Vegas, you do not have a 120% chance of losing. Okay, but you can get close to 100%. This is in a nice situation where there are no greens. So it's actually worse in real life. And as a nice exercise, you can easily tweak what the probabilities would be instead of being 1/2 every time. It's a nice exercise to just see just how bad things are. Here's some code to just plot what's going to happen. So I am writing a little program to simulate a game. So capital is how much money I start with, spins is how many spins I want to do, and I want to see how much money will I have when I'm done. So loss is going to be 0. Now, when you look at this code, what's the first thing you notice that's missing? Comments, right? Thou shalt comment, right? So results, I'm going to store results, n goes from 1 to the number of spins, n plus plus, so I'm increasing n by 1. So this is the main part of the program. And I'm going to keep going through here, and here's the end of n. Okay, there was a comment. And then if my money is greater than 0, what do I bet? I'm going to bet my loss plus 1. And if my money is not greater than 0, I'm going to just bet 0 because I have no money to bet. And I'm going to choose a random number between 0 and 1. If it's less than 0.5, I'm going to declare myself a winner. And if it's not, I'm going to declare myself a loser. So I'll set win to be 1 or win to be 0. And then if win is 1, I take how much money I had and I add the bet. And now I set loss to 0 because I haven't lost any in the vote. If I lose, then I have my money is my money minus my bet, and I increase my loss by the bet. And I append the result to a list. So I initialize results to be, these braces means it's an empty list. And I'm going to append to it n, and then result. So the x-axis is going to be the spin number, and the y-axis is going to be my net worth at that spin. So do you want to see what happens when I play this? So here is an outcome. So I'm doing pretty well. Things are going nicely, crash, and then I have a negative amount of money and I can no longer bet. For a while, I was doing really well though. What should I have done differently?
Stop playing.
When?
Or you lost your money.
So if you can see into the future, then this is when you stop playing. Most of you cannot see into the future. If you can see into the future, let me know. Does anybody know the TV show where in the roommate agreement, one of these small codicils is that if either one ever builds a time machine, the very first thing they will do is return to this moment in time plus 5 seconds.
It's a Big Bang.
It is Big Bang Theory. Well, Sheldon, when he's making the new roommate agreement with Leonard and he's meeting him, one of the agreements is if either one of us ever builds a time machine. So when Leonard signs it, you should. Oh, that's unfortunate. I'm assuming nobody's able to build a time machine. So the problem is you don't know when you're going to start to do poorly. What could you do to prevent yourself from crashing like this?
Quit as soon as you make it.
So one thing is to quit as soon as you make any money, in which case we're not going to make a lot of money. That's one possible strategy. What else could we do?
You quit as soon as the next roll would put you below.
So you could basically say, I'll stop here. I can't afford to go any further because that could make me negative. So you could do something like that as well. And so you may end up losing money, but you could put in a floor that I will not go below a certain point, that I'm going to limit my losses. This is why you do not want to be in a place where they advance you credit in Vegas. I've been in the Vegas airport and they have the slot machines and they've changed over the years. In the old days, they used to spit out the coins when you won. Now you have an electronic credit. Why is it better for the casinos for you to have an electronic credit?
You can't visualize.
You can't visualize. You don't have the money in front of you. And so you're more likely to keep playing. So there's a lot of wonderful human psychology that goes into this applied probability. Right? Later this semester, people interested, we will talk about counting cards and blackjack. And so the first mathematician who really came up with a good system and published it was actually contacted by, we will have a equipment malfunction soon, by certain gentlemen who said, we'd like to fund you. And now he's in a very difficult situation. He either offends the gentleman who wants to fund him, or he now uses math to go to the casino, and he might offend the people in the casino. But what's nice is if there's ever a misunderstanding in Vegas, there are some very nice rooms where you can have a conversation without fear of being interrupted and just work out any misfortunate understandings. So be very careful in applying stuff like this. If you've seen the movie 21, 21 is fascinating in terms of how they try to apply card counting by having multiple people involved to try to minimize exposure, trying to disguise things. Vegas has some of the best facial detection software in existence because there are certain people that they do not want in their casinos. They now have frequently 6 decks that they go through, and they do not go all the way through the decks because some people are good enough card counters, they can get a slight advantage in some games like blackjack. There are people who have bought the same card shuffling machines that are in Vegas and have done analyses of these to try to get a sense of what is the probability of getting a certain shuffle if you know how the cards are dealt and picked up, to get some sense of where is a card likely to be. There are a lot of times very small things you can exploit. If there's more time, I guess we'll have to do another lecture. I will talk about some game shows where they did not use random number generators, they used almost random number generators, and people were able to take advantage of that and win 6 digits. So this is our first lecture where we're actually applying probability to analyze real world problems. We've got the difference equations and population dynamics with random variables, and we've got the lift. So we'll do one more lecture on this stuff tomorrow. And tomorrow, of course, means Friday.